Alright, now this week and next week we're going to cover gastrointestinal infections, and it's really hard because there are so many possible causes of gastroenteritis, in other words diarrhoea and vomiting. I'll cover the ones that are important globally as well as important locally, but you can't cover all of them. There are so many of them. So first thing is, what do we think of about as diarrhoea? It's really hard because what's diarrhoea to me may be not diarrhoea to you. It depends what your normal bowel habits are like. But if you understand that we ingest up to 8 litres of water per day, and most of that is absorbed in the bowel. If your bowel is upset and not absorbing water properly, then you pass out as feces, you get runny stool. So overall, we talk about diarrhoea as being, more than frequent production of feces, normally less solid or more liquid. It may or may not have vomiting at the same time, and you may or may not have abdominal pain and cramping. All depends on what the cause of diarrhoea is. Some causes just make the bowel stop absorbing water, and you have loose stools but with no cramping. Other bugs actually invade the bowel and cause ulceration and local damage. That causes cramping, and then you have diarrhoea as well. So it may be just diarrhoea. It could be diarrhoea and vomiting, it could be diarrhoea, cramping and vomiting, and it may also have pus and blood in the stool. And again, it all depends on the organism that's causing the infection. So overall, we can look at the causes of diarrhoea in 2 broad categories. Sometimes they're non-infectious. They're caused by things that you eat that you don't like. Certain foodstuffs can make your bowel upset. I know if I drink red wine, I get diarrhoea because something in red wine and my bowel just don't agree together. So it may be totally non-microbial. There's increasingly, we recognise that it may be caused by an infection, but something we don't even know exists yet. So, since I've been trained as a microbiologist, there's been 3 or 4 new causes of diarrhoea that weren't even around when I was being trained. They were obviously around, but not discovered yet. So there are things out there now that cause diarrhoea. We can't find them because we don't know what they are yet. So these are things that will be discovered as time goes on. But right now, amongst the things that are infectious, some are parasites, some are viruses, and some may be preformed toxins that you ingest. This is a toxin that's made on the food. You eat the food, you're never infected, but the toxin you ingest is active and can cause usually vomiting very, very quickly, and then maybe diarrhoea as well. Most of this course is concerned with this bottom section. That is, it's infectious and it's caused by bacterial infections. Of the bacteria that we know that cause gastroenteritis, some cause disease by invasion. Now, invasion doesn't mean invading the bloodstream. It means invading locally the cells that line the gut. So they invade enterocytes. Sometimes they don't invade at all, but they attach to the cells in the bowel and from there produce toxins, and the toxins are active and make the bowel stop absorbing water, or maybe make the bowel secrete water, all depends on the toxin. Or the toxin may cause the cells to die and ulcerate. And a small number simply attach and irritate. In the end though, all these things here cause the bowel mucosa to lose its function, which is primarily to absorb water. And then you get diarrhoea. There's a whole range of possibilities for the epidemiology. In other words, epidemiology is where does the bug come from initially and how does it get to you to cause the disease? That's epidemiology. Most commonly it'll be food or water that's contaminated with faeces. And the faeces might be human, but more likely it will be animal. Animals are a major source of foodborne disease. Sometimes it might be hands or objects that are contaminated with faeces when you go to the toilet. That's a fairly small component of all foodborne diseases caused by poor personal hygiene. It's really, really unlikely. It's much more important to see other mechanisms. And again, sometimes food might become contaminated with faeces via flies that land on faeces somewhere and on the food. But by far the biggest situation is food or water that's got contamination with faeces, probably from animal origin, much less human origin. So we think now about animal faeces in the food chain. Lots of things that we ingest that cause diarrhoea have got the organism on them from animal feces as part of food production. So cows carry salmonella. When you slaughter a cow, not that I'd ever know, 'cause I've never done one, but when you see people slaughtering cows, there's lots of feces around because the animal is killed, it defecates, and when you slaughter the animal and you cut the carcass, that's a point of contamination. I mean, a piece of steak is just muscle, and muscle is sterile. There can't be any salmonella in a piece of meat unless it gets there after the animal dies, because it's sterile tissue. So it's during slaughter that we see the tissue become contaminated with feces or fecal material that contains salmonella, for example. Or when you kill chickens, chickens often carry Campylobacter, major cause of diarrhoea. Now, a chicken is different because with a chicken, we buy the whole carcass. And even though it's been gutted, the inside of the carcass still contains, or still may contain, some Campylobacter. So these are bugs that don't necessarily cause disease in the animal, but contaminate the tissue that we then ingest. Eggs, even when eggs are being produced, there's now evidence to suggest that sometimes during egg production in the chicken, the salmonella is actually enclosed inside the egg shell. So one risk is they pass the egg and the egg's dirty on the outside, and even when you wash the egg on the outside, unless you're really, really careful, there may be either salmonella or Campylobacter on the outside of the eggshell. But now we understand that in some cases the salmonella is enclosed inside the eggshell with the eggs being produced. So lots and lots of exposure, because lots of animals that we ingest as part of our food system has possible contamination. So I would say that exposure is really common. We are exposed to salmonella much more than you think we are. So why don't we always get sick? The issue is you need to have a certain dose to get disease, because our stomach acid is protective. And even the large number of normal flora inside our bowel means that the small numbers that get through into your bowel when you ingest them can't compete, can't attach. So you need a minimum dose to normally cause disease in a healthy individual. So it will be different if you're not healthy. If there's some issues about your bowel integrity, then you may require a lower dose. But for most people, it's a large dose. The reason that if we have a large dose required, that's why food's often important, because a small amount of contamination on a bit of food becomes a large number if the food is kept warm for a fair period of time. Remember, these bugs multiply every half an hour to an hour and double in number. So a bit of food kept at room temperature or warmer than that even, you can imagine in 4 or 5 hours, a small dose becomes a much larger dose quite quickly. So food really is a potential to amplify the starting dose of infection. Oh, wrong one. When you think about the fecal oral route, everyone kind of thinks, oh, you know, everyone's going around directly eating feces, but it's so indirect. There can be a tiny amount of contamination on your fingers, on your hands. That's transferred to food. Food amplifies the signal. So most foodborne disease ultimately has the fecal oral route, because the bug comes from a feces somewhere, either human or animal, ends up on your food by some mechanism. So the overall route will always be fecal oral, almost always. But how it gets there is, you know, is quite variable depending on the organism. Here's a range of some of the organisms we'll discuss this week and next week. All of these either do commonly cause gastroenteritis or can possibly cause gastroenteritis. So starting at the top, Campylobacter, very, very common cause of gastroenteritis. The number one cause in Australia. It's not a coliform. It's a gram-negative rod that's oxidase positive. It's a bit like a Vibrio organism, but it's not an Enterobacteriaceae. Salmonella and Shigella are both Enterobacteriaceae, and they both are non-lactose fermenters. And these are the bugs that led somebody a long time ago to invent MacConkey agar, with lactose as a differential agent because they want to separate these two from everything else. MacConkey agar was primarily designed to separate Salmonella and Shigella, non-lactose fermenters, from E. coli, which historically was a lactose fermenter. It was a way to screen your poo for possible Shigella and Salmonella. It's become more widely used than that now, but initially that's what it was there for. Yersinia is also an Enterobacteriaceae, but doesn't have the same kinds of rules that we have with Shigella and Salmonella, so you find that by a whole different approach. It's fairly uncommon. So the first three are looked for routinely in almost all laboratories. Yersinia will depend on where you work. Most labs these days have given up because it's very hard to find and not very common. Aeromonas can cause diarrhoea, but the problem with Aeromonas is sometimes you grow it in somebody without diarrhoea. So when you grow one, you can't be sure it's the cause of the person's symptoms or just happens to be there. So again, a lot of labs now have moved away from doing Aeromonas. And Aeromonas, again, is not Enterobacteriaceae because it's oxidase positive. The huge one that's become, and when I was training, it was really an occasional thing, and now is a global nasty, is Clostridium difficile. This is a horrible, horrible cause of diarrhoea. It causes disease mainly in hospitalised patients, not always, but mainly, and is mainly linked to recent or current antibiotic therapy. So really we call this disease antibiotic-associated diarrhoea. And something about having recent or current antibiotic therapy changes your bowel flora in such a way that if you're exposed to Clostridium difficile, it becomes established and causes disease. It makes a lot of toxins, and it's had a number of mutations over the last few years that have made it produce a lot more toxin than before, so the disease is much worse, and it's become highly antibiotic resistant, which means it's very hard to eradicate when you get it. We'll talk more about that next week. E. coli, lots of E. coli's cause diarrhoea, but because the majority of E. coli's don't cause diarrhoea, separating out those ones in your bowel that do cause diarrhoea from the ones that don't cause diarrhoea is really challenging. So labs find it very hard to efficiently and reliably detect diarrheogenic E. coli's compared to normal E. coli's. So routinely it's unlikely. It would require history or some suspicion before you look for these kinds of E. coli's, and then it becomes very complicated. Vibrios do cause diarrhoea. They're classic causes, as well as Vibrio cholera, which causes epidemic diarrhoea. There'll be other Vibrios, or there'll be Vibrio cholera that causes just sporadic diarrhoea. Labs look for Vibrios if they're in an environment where they're common. So in Australia, we tend to hardly ever look for Vibrios because they're not common in Australia. Parts of Asia, they're an extremely common cause of diarrhoea and would be routinely looked for. You live in Japan, then Vibrio would be a common cause of gastroenteritis and would be a routine pathogen you look for. You work in India where cholera is endemic, then you would always screen for Vibrio cholera. So it depends on where you work. Some things are in that area, some things are not in other areas. In Australia, Vibrio is uncommon. I think there are reasons why, in many cases, there's no point looking for the cause of gastroenteritis. So in this room, in the last couple of years, I guess we've all probably had an episode of diarrhoea. Been sick for a couple of days, or might have had some vomiting. How often do you go and seek a GP and say, I've got diarrhoea, can you please diagnose this? So the first reason you go see a GP is you want a certificate to get off work or out of uni. But you don't get diagnosed and treated because most times diarrhoea is self-limiting. So the need for diagnosis, specifically what the pathogen is not always there because most times we don't need to know. Because treatment for most people does not assist recovery. So if we treat you with antibiotics, when you've got diarrhoea caused by, for example, Shigella or Salmonella, antibiotic therapy often doesn't help. And in fact, in some cases, having antibiotic therapy can prolong the period in which you shed the organism, even when you become asymptomatic. So antibiotic therapy is only recommended and only useful in specific cases, elderly people with severe disease. But for most young people with diarrhoea, even caused by Shigella or Salmonella or Campylobacter, therapy is not helpful. So a lot of time there's no need. The reasons we do have a culture where we do want to try and find out what the cause of diarrhoea is, sometimes there's public health implications. Now, if I get Salmonella food poisoning from something that I've eaten, and it's a one-off, no one really cares. But if I get food poisoning from a Salmonella from a thing I've purchased from a bakery or a shop somewhere or a butcher, and you get it, and someone else gets it, and somebody else gets it, we need to know that we're all exposed to the same source, because then we find out where the problem was, and we go to that shop and have the food removed, find out how the contamination occurred, and we problem solve and stop it at the source. So one of the big pushes for diagnosis of diarrhoea is to find the common source, if it's a common source. But often it's not. Most cases of food poisoning are simply sporadic, and they occur from contamination in your own kitchen, in your own house. But when they occur somewhere else, at a common source of food production, for example, then it's important that we find out. And there are so many outbreaks that you only find out because a range of people from different areas have gone and sought help. They all had this weird bug, and we've gone back and found the common factor. Oh, they all ate at this restaurant, and they all live in this suburb with this bakery. So there's ways to do that, and you can't start that investigation until you have all the information about who's got what from their diarrhoea. So if we accept that sometimes we will look for the cause of diarrhoea, although most times we won't, if you do decide to try and diagnose the diarrhoea accurately, what you have as a specimen is faeces. We never, ever, ever accept a rectal swab. Doing a poo in a jar is not that hard. It's probably less traumatic than doing a bum swab, because it's normal to do a poo. It's not normal to have a swab up your bum, is it? So it's normal. So we don't want swabs. And pathology labs do not culture food. There are lots of reasons why we can't culture food. The biggest reason is the techniques required for food culturing are quite different than those required for poo culturing. Whole different range of plates, different approach. And our labs just aren't geared up for doing food culturing. That belongs to public health laboratories, not for a path lab that does human diagnostic work. The other issue is just growing a Salmonella from some food doesn't prove anything. When I first started working here a long time ago, and we had plenty of spare time back then, and we had less pressure to do things quickly in a hurry, one of my practices in micro was to go down to the supermarket and buy a couple of chickens from the supermarket and bring them back and culture them. You'd be amazed how often we were able to culture Campylobacter or Salmonella. The bug is not uncommon. Growing it from food, it doesn't mean anything, because our culturing systems are so sensitive, we can grow incredibly small numbers. We can swab the chicken, put it in a broth, wait 24 hours, amplify all the bugs selectively, culture them again, get the Salmonella. It's easy to do that. Does that mean that that chicken is dangerous to somebody? Does that mean that that contamination caused someone to have diarrhoea? Unless you're able to link that bug in the food with the bug in someone's faeces, you've proved nothing. So we don't do food. How do we know what to look for? When you look at so in Australia, when you do pathology tests, the government will reimburse the laboratory for the cost of the test through the Medicare system. And there's a schedule, great big book, that tells you what the government will give you for a certain test. And for a midstream urine, we might get about $20. I don't know what it is, top of my head, don't know, have no idea. But normally you want to make sure that whatever you're doing in your laboratory is covered, cost-wise, by the money the government gives you. Otherwise, you're spending $40 on a test, government gives you $20, as a company, you go broke. You've got to make sure your tests cost less than what the government reimburses you, otherwise you don't make any money. The dearest test, or one of the dearest tests, is culturing faeces. It's very expensive because to do it properly requires looking for so many different organisms. So it's important that you try to limit the things you look for to what you might find. It's great to go and look for Vibrio cholera in every specimen, to find one every 5 years. The cost benefit there is so pathetic you wouldn't bother. So we look for things that we know are quite common, and maybe you might increase that range of what you look for depending on what's happening locally. So if there's an outbreak at the moment of, say, Vibrio somewhere, you'd include Vibrio, but you wouldn't worry about Vibrio routinely. History can be important. If I've got a patient who's come back from travelling in Japan or somewhere else in Asia, you might go, well, perhaps in that person, it's worthwhile doing a screen for Vibrio. They've been somewhere where it's endemic. So where they've been is more important than where they are right now. So you may change what you look for. The one thing which can be helpful sometimes, but is probably overrated, is the nature of the stool. So, for example, if I see the stool being full of pus and blood, I get excited about that because it's going to find a pathogen there. And maybe if the stool is bloody and full of pus, that might make you think more along the lines of Clostridium difficile, because we know that bug causes bloody diarrhoea. But so often you see somebody where you grow a pathogen and their poo was not bloody, wasn't even runny, just a hard bit of rock. That would be full of pathogens. So the things that determine whether your poo is runny or hard as rock is A, what's in your bowel and whether you've got infection or not, but also how much you drink. And if in the previous 24 hours you've not drunk much and you're dehydrated, your stool will be fairly formed. So a formed stool does not exclude it being infected. But on the other hand, stools with pus and blood tend to have a high yield of organisms. So the majority of our stool is actually water plus bacteria. That's what it is. And if I can show you in the practice next week a gram stain of faeces, you'll be just amazed about just how many organisms are there. So think about your mouth swab. You saw a few cells and lots of bugs. Well, a fecal gram stain is just worse than that. It's just complete wall-to-wall bacteria. That's all it is. So we're looking at an average of about 10 to 12 bacteria per gram. Enormous numbers. And I hadn't thought about this much before until students often ask me, oh, when you get salmonella, is all the bug in your bowel salmonella? The answer is no. When you have infection, the bug causing disease is still only a small proportion of all your bowel flora. It does not dominate in most cases. Sometimes it does, but most times it doesn't. So it may be that if you've got salmonella food poisoning, for example, or Campylobacter, for example, you might have one pathogen in every 10,000 normal organisms. So now we're going to try and find a way to find a 1 in 10,000 that are normal. How do you find that one bad organism? It becomes technically quite challenging. So can we do direct microscopy on a fecal sample in the same way we do it, say, from a sputum specimen? And the answer is no, because most times the pathogen, A, is there in small numbers compared to what's normal, and the morphology is not distinctive. If you see a person's bowel who's got salmonella food poisoning, what they have in a small number is a gram-negative rod, salmonella, in amongst 10,000 E. coli, which are gram-negative rods. So you can't see anything that's abnormal. It's pointless. Very occasionally it can be useful. If you have Vibrio, the organisms are small and curly, and normal bowel flora is not small and curly. So seeing small curly gram-negative rods can be indicative of either Campylobacter or Vibrio. So it can be useful. Most times we culture. And we culture on plates that are selective and differential. We want, first of all, to inhibit as much as we can all the normal flora. Remember, it might be one pathogen in 10,000 or more than that of normal. The more you inhibit of what's normal, while you retain the viability of your target organism, the better it is. So plates must be selective. And it helps if something about your target organism looks different on the plate than your non-target organism. So historically, MacConkey AO was chosen because it was differential. If you're a non-fermenter, it meant you might be Shigella and you might be Salmonella. But if you're lactose positive, you couldn't be Shigella and you couldn't be Salmonella. That's how it works. Plates these days are getting much better at being more differential than simple one colour change. But that's the basis on which we do the tests. And we are getting better at doing things not by culturing. Why is there a push away from culture? Not because we hate doing it? No, I love doing it. It's great fun culturing stuff. What's wrong with culturing? Too slow. Time is the killer. 24 hours is an absolute minimum, but most likely 48 hours, often 72 hours to find something. I want to know what the answer is now. So PCR, as usual, has become a very common way to detect certain organisms, but only if you can find a target which is very specific and covers all subtypes of that organism, and that can be very challenging. So there's still no good PCR for Salmonella because it's too variable. You can't find one single target that they all have that all the other bugs haven't got. It's difficult. But we do PCR for things like Clostridium difficile because that as an organism has got a number of targets that are really useful targets for PCR. So let's just move on now and look at our first organism. So we'll cover Shigella, we're going to cover Salmonella, we'll cover E. coli, we'll cover Vibrios, and we'll cover C. difficile over this week and next week. So Shigella, first of all. If you went back in time and you redesigned the whole system of nomenclature, Shigella would be called E. coli. Shigella is so closely related to E. coli, it's not funny. And there are some strains of Shigella and E. coli that you can't separate. And there are now some E. coli's that cause disease in the same way that we see Shigella causing disease. They're very closely related with a few key differences. So there are 4 species of Shigella: Dysenteriae, Flexneri, Boydii and Sonni. Of those 4, the one that causes the worst disease is Dysenteriae. And as the name suggests, you get dysentery. And dysentery, by definition, is very runny stools with pus and blood. Most of the species of Shigella have plasmid-mediated invasions. An invasion is basically a protein that they produce that lets them invade the cells that line the gut. So they're locally invasive, not systemically invasive. You hardly ever see Shigella in the bloodstream, but it can invade the cells of the gut. And when it invades the cells of the gut, the cells ulcerate, and you get ulcers in the bowel, which is where you bleed from. And when the Shigella invades one cell inside the gut wall, it can then invade the next one by going through the side wall to the next cell. So you end up with these growing little ulcers in the bowel. What's unique about Shigella is it's one of the only ones that we see commonly causing human disease that only has a human reservoir. No animals have Shigella. It doesn't get on food during food production because animals don't carry it. Shigella is always linked to contamination of food by the person who's infected. Let me just make sure I cover this. The 5 F's, which we talk about for Shigella, and I always get the first 4 and forget the last one. Food, fingers, feces, flies, fomites. Now, the issue with Shigella is, compared to other causes of gastroenteritis, Shigella requires only a small dose. You can get Shigella infection from ingesting a sew of 100 organisms. Yeah, with salmonella it would be in the thousands. So it's highly infectious, but less common because it doesn't occur in food naturally. So you have someone who's infected, they go to the toilet, poor hygiene, next thing you know it's on their fingers. They touch you, it's on your fingers. They touch an object, like a fomite, something that you share, a toothbrush, or something else that might be involved in the kitchen. Flies, clamor, feces, you can go from there to food. In the end, we need some mechanism to get a small amount of organism from that person who's infected into your mouth. And those 5 F's are what does it. It's fingers especially. Now, I wonder where we see the most cases of Shigella infection. What kind of environment would you want to see that? If somebody in this room right now had Shigella, I would hope that we'd all be pretty safe. Because you're all pretty clean, and you've all got good skills in going to the toilet, because you're all old now, aren't you? If I went right now with a swab and got hold of your right hand, if you're right-handed, and cultured you, I wonder how much I'd find of E. coli. Hopefully not very much, because we've all done things properly, washed our hands, used soap and water, the whole lot. But where wouldn't that apply? Children. So we see outbreaks of Shigella in daycare centres, anywhere where kids are congregating, because one kid with poo on their fingers means nothing if it's just one kid. But if it's one kid mixing with 20 other kids, then there's a risk. So we see outbreaks in daycare centres, kindergartens, and sometimes towards the end of life in aged care facilities, because in those situations there's a lot less control of defecation and less hygiene. We don't often see outbreaks of Shigella, because outbreaks normally imply there's going to be food involved somewhere that's consumed by multiple people. With Shigella, there'll be small little outbreaks linked to one person who's infected, who passes it on to other people during one episode. So, okay, you're unlucky. You got Shigella food poisoning or Shigella infection. How do we find Shigella out of your bowel? Well, we culture your poo. And we culture it and we look for things that are non-lactose fermenters. So in your bowel, if we grow coliforms, forget all the rest. I mean, in your bowel there's thousands and thousands and thousands of organisms, and at least by a ratio of 1,000 to 1, they're anaerobes. But forget them. If I just culture your gram-negative rods that are facultative or anaerobic on a concrete agar plate, there's 2 types, lactose fermenters and non-fermenters. If the bug is a lactose fermenter, it can't be Shigella and it can't be Salmonella, kind of speaking. That's the rule we use. Isn't always true, but it's not a bad rule to start with. But when you grow a non-fermenter, it does not mean it is Shigella or Salmonella. The majority, by a massive margin, of non-fermenters in the bowel are not Shigella and not Salmonella. They're simply non-fermenting E. coli's or proteases or citrobacters or anything else. Lots of bugs that are lactose positive have some variants that are lactose negative. But our first point of call is we culture the poo. If the colony is lactose positive, we know and we accept can't be Shigella, can't be Salmonella. The ones that are lactose negative, we say they might be Shigella or they might be Salmonella. but they're probably not. And then we go through a whole series of other screens to further separate those non-fermenters into not Shigella and not Salmonella, and then possibly Shigella, possibly Salmonella. And we do it again, stepwise fashion. The key things about Shigella that make it different from other bugs that are non-fermenters of lactose is it does not make gas from glucose, and most other bugs, when they ferment glucose, make gas. This doesn't. It's a very old-fashioned test, and these days almost nobody cares about gas from glucose because it's tedious to do and there are better ways to do it. The really good thing about Shigella is they're always non-motile. If your bug is motile, it's not Shigella. That's a really useful test. And if your bug is urease positive, it's not Shigella and not Salmonella either. So after a whole range of screening procedures that might take you one day each time, after 2 or 3 days, you're at the point where you think, yep, this non-fermenter of lactose might just be a Shigella. Then you go and do your full identification, either with an API. MALDI-TOF is still not very good at doing Shigella because it's so closely related to E. coli that the profile you get is not that reliable. So always with Shigella, once you have an identification based on biochemistry or protein profile, if it's a MALDI-TOF, you always do serology. Because ultimately, the one thing that separates Shigella from other E. coli's is the surface antigens. And you can buy polyvalent antisera that covers all Shigella. But given that there's only 4 of them, most labs have a bottle of antisera for Dysenteriae, 1 bottle for Flexneri, 1 for Sony, and 1 for the other one, which, what's the name of the other one? There's 4 of them. I always forget the last one. So you might have 4 bottles of antisera. Get your colony onto a slide, add antisera, rock it. Yep, look at notes. It's that one. And you can't report Shigella to a clinician without having positive serology. The biochemistry is not reliable enough without serology. You must do serology first, at the end. So there's Shigella. Pretty easy to deal with. And also, you know, if I look at Tasmania, for example, I would say that on an annual basis, the number of cases of Salmonella reported compared to Shigella would be 1,000 to 1. Salmonella is very common, Shigella is very uncommon. So now let's think about Salmonella. It's the second most commonly reported cause of gastroenteritis, second behind Campylobacter. And depending on the person and the dose and the particular strain that you have of Salmonella, you'll get diarrhea and vomiting, but only sometimes you have pus. So pus and blood are a common feature with Shigella, but less common with Salmonella. It doesn't really invade to the same degree that you see with Shigella. So you don't get ulceration and blood loss in the same way. You may get inflammation, which is why you get some pus, but less commonly see blood. Blood's uncommon in the stool with Salmonella. And again, compared to Shigella, this requires quite a large dose and is most commonly linked to some kind of animal, an animal reservoir. Chickens, cattle, some reptiles can carry Salmonella, and some people as well. We see most cases in children under 4. Now, I wonder why that is. Probably a whole range of reasons, but one reason why kids under 4 we get more Salmonella than adults. Let's think. I wonder how many kids under 4 eat food different than their parents. Well, not that many really. I mean, your kids eat what you eat. So why would they get it and you wouldn't get it if you're eating the same food? because they're naughty and they deserve it. So this karma means they get it and we don't get it. It's got to be a better reason than that. Yeah, so one reason is they're diagnosed more often because kids get sick and we panic. Oh, they're sick, take them to the doctor. If I'm sick, I just go, giddy, not going to work today, I'm sick. So it's probably diagnosed more often. But there's also a true component where they get more disease than we do. So one thing is we all get the disease, but they're reported and diagnosed, and we're not because we're older and healthier. But also their stomach acid is less strong, so they require a lower dose than we do. So they get more disease because of the lower stomach acid, therefore require a lower dose of organism. And when they're sick, they probably get more sick than we do and grizzle more, and parents tend to over-doctorise their children. Compared to Shigella, this requires quite a large dose. But again, because it's a foodborne organism that's common in food in the food chain, it's often linked to food, which is where you can get the higher dose. The idea that people can be carriers of salmonella is probably a bit overrated as a concept, really. A small number of people do get disease with salmonella and do become carriers. In other words, they recover and keep shedding the organism. It's much more common with Salmonella typhi, as in Typhoid Mary. Please tell me somewhere in your school life you've heard the Typhoid Mary story. I just forget how much stuff that was just commonly told as just a story doesn't get told anymore. And I hate telling things where everyone just goes, I've heard this a million times before, Tristan, just shut up, I've heard it before. Has anyone heard the Typhoid Mary thing? I'm so sad for you that you don't hear this stuff. So, historically, go and Google it, the Typhoid Mary was a person, this might have been a cook, who got typhoid fever. And typhoid fever is a particular kind of salmonella. And because she was a long-term carrier, and she was also a cook, everything she cooked was full of typhoid organisms, and it spread massively, and she became quite infamous as the source of this massive outbreak of typhoid fever. So in the microhistory world, Typhoid Mary is, she's a massive figure. Just Google it, Typhoid Mary. It's not a bad thing to read. Take you 5 minutes. It won't kill you. I might even put it in the exam just to annoy everybody. But that's a unique case because with Salmonella typhi, which we'll talk about shortly, the bug gains access to your gallbladder, where it can sit there and be shed in small numbers for a long time. For most people, their salmonella is not Salmonella typhi. So typhoid fever and Salmonella typhi is a whole separate category of salmonella. It's separate disease. Should have a whole different name, but it's not. Normal routine salmonella, you ingest the bug, if you're unlucky you get sick, you have diarrhea, you recover. But you do, everybody still does this, you recover but shed the organism for a number of days or a week or so after you recover. I don't call those carriers. They're just shedders who are shedding in the convalescent phase of their disease. A true carrier is somebody who gets disease, recovers, but keeps passing out salmonella for months and months and months afterwards. That's a carrier, and they're uncommon. But I do know that a long time ago, we used to do screening of people that worked at the abattoir. So where they kill all the cows for all your steaks, the meatworks, if you're in that environment, that you're always ankle deep in cow shit. That's what your job is. So you're exposed all the time. And these people would become infected, but not even get disease, but become carriers. We had meatworkers who were carriers of salmonella. And in those people, they would treat them to try to remove the carrier state. So overall, carriers are not common. A true carrier means no disease currently, but I'm still shedding the organism. I remember having this discussion before with nursing students, and I quite like this discussion. If you're in food production, so you might be a chef, and you have salmonella. So you're a chef and you've been identified as a carrier of salmonella. Should you keep working or should you stop working? Now there is no right answer, by the way. Now, most people straight away go, stop working. Now, if you are on the side of, this assumes they're not sick. Like if they've got diarrhea, it's different. But if they're a carrier, that means they're also going to be well, but they're pooing out salmonella every now and then. If you say keep working or stop working, so if you say stop working, what you are saying is you think it's inevitable that that chef will somehow transfer some of his feces onto your food. That's the only way it's a risk to you. Right? That's what it means. If you say stop working, that means you assume it's going to happen. Doesn't it? If you say keep working, that means you assume that things in that kitchen are so well organised that a chef will never transfer his species to your food. If you vote for this one, stop working, that means all the chefs out there that are not carriers, you're okay with the fact that their poo ends up on your food. It does mean that, doesn't it? If you believe this is the only way to deal with it, it means that every other time it's okay. Thanks, mate, for that. So I think this is the right answer. It's only my opinion. Because I think you'd have to assume that in a kitchen there's enough things in place that mean you won't get any of that person's fecal material onto your food. If they were sick, it's different. Because you're in there making up someone's steak and you've got to go to the toilet and you brush out and you've got the runs, it's much harder to control that. But for a carrier, it's quite different. Here's an idea of how complicated it can be with something like a foodborne organism. So salmonella is common in a range of animals. This is a range of possibilities. So you have one person who's got sick. So you've got salmonella food poisoning, you go to your GP and you get diagnosed. And then you go home and say, oh, Mum, I've got salmonella. And your mum goes, oh, where did you get it from? And you go, oh, it was the pie I had last night. You know, or was that bloody hamburger I had? How would you ever know? Because look at this. Wild animals can carry the organism. And sometimes those wild animals get their feces into water. And then this water might go into food that we eat. Or we might drink the water. Or it may be an animal that you've touched. A pet snake, pet lizard. They carry salmonella into you directly. It can be food that's been made from an animal like a cow in an abattoir that you eat the food. It may be something that you've touched that's giving the salmonella. So this one person with disease could have come from anywhere. A massive big chain. You can't find the source of disease for an individual case. The only way of finding the source is if more than one person has the same specific strain of disease and you find a common factor to all of them. It's very hard to find the source of organism. And sometimes, even with very, very big investigations, they say it could have been this, that, or that. But we can't be sure which one it is. It can be hard to sort them out. So you'll see things all the time. Now, the one at the very top there, it was a bakery at Trevellyn, just around the corner from where I live. And that was a massive, big problem. And in this particular case, the contamination occurred not at the bakery, but at a supplier of cream to the bakery. But they had, I mean, it ruined their business. For 6 months, their business was stuffed because of one outbreak. You can imagine if you've got a bakery and all of a sudden it's in the paper that your customer's got salmonella, you're going to go somewhere else, aren't you? Inevitably, you're going to go somewhere else. I have no idea what your impression is with salmonella, but I know when I was growing up, before I came to university and studied about microorganisms, I used to think, oh, salmonella, that's deadly. But the reality is, salmonella gives you diarrhoea and vomiting, and you aren't very happy, but you don't die. When you see these kinds of headlines, I mean, this was sad. This is a nursing home, and I think 5 residents died in the nursing home because in the nursing home their food was contaminated, and a lot of them got diarrhoea, salmonella, but 5 of them died. And straight away it's like they were killed by salmonella, and they kind of were, but they kind of weren't. They died because they were dehydrated and they were very old, and the salmonella just tipped them over the edge. These were old people. They didn't deserve to die. I'm not making light of this, but salmonella does not kill healthy people. It kills really old people or very young people who are already at some risk because of their situation. For most people, it's just a cause of diarrhoea. Not very nice, but it's diarrhoea. It's not the killer that everyone seems to think it is. I'll just finish off this bug and then we'll stop. Now, with salmonella, there are thousands and thousands and thousands of individual subtypes of organism. And for various reasons, we want to know which specific subtype in those thousands and thousands you have. Because the only way to link your disease to somebody else is if you have the very same specific subtype. So we subtype them based on serology. We have anti-sera that target specific antigens on the surface of every salmonella organism. The way in which we name salmonella is quite confusing. Historically, there were 3 species. Typhi was always separate because it causes a whole separate disease. It's not just salmonella food poisoning, it's a whole separate disease. So that deserves its own status. And then there was one called Colarocilus. I never quite worked out why they got its own species name. And then there was one called Enteritidis. But in this one species, there were 2,500 different subtypes. And for every one of these, you would look at their antigens on their surface, and on the surface of a salmonella, there's 2 kinds of antigens. There's ones on the flagella, called H antigens, and there's ones on the cell surface called somatic or O antigens. So there's always an O and an H. H is flagella, O is cell surface. And the flagella ones can be in more than one phase. So when they make the flagella, they can be in phase 1 or phase 2 flagella production, and different antibodies react with it. In short, for every single strain of salmonella, you have a profile of a number of different loci for positivity. So this one is positive for 1 and 4 in the flagella, and positive for little I and 1 and 2 on the surface. It's complicated, doesn't matter. It's not your job, it's done somewhere else in the reference laboratory. But this ends up being a fingerprint for this particular serotype of this species. So when you say the term, I've got disease by Salmonella virchow, what that really means is you have species Enteritidis, and that's the subtype. This is not, strictly speaking, a species name, it's a subtype, and it's given a capital letter. But in routine, normal, everyday language, we think of this as being a separate species. Academically it's not, but in practice we think of it that way. And it does make sense to me, it's just normal. What they now have is a whole different system. There's now just one species, and in that species they have 6 biotypes, and then within the biotypes there's Enterica with all those different subspecies. So this replaces that. In the end, I am happy if you don't care, because I don't care either. I would not examine you on the ins and outs of the nomenclature. It's complicated, and it's really designed to satisfy taxonomists. In everyday, normal working language of a laboratory, there are two kinds of salmonella. There's typhi, separate disease, and there's all the rest. When you see a certain name for a salmonella species, it's not really a species, it's a serotype. But it doesn't matter. For us, it's the same thing. So what we see now as a routine is we tend to keep this one separate because biochemically, an API or a multitoph will give this one separately, easy. It'll come out and it will flag it and go, this is a typhi because this is a big deal. And then there's a couple of others. Paratyphi gives a disease which is a poor man's typhoid fever. Cholerasilus can be invasive and cause bloodborne disease. Then there's the rest. This is kind of a quick shorthand way to show you why we care about doing serotyping. So what we're seeing on this overhead is people at two houses and they're getting diarrhea, and when you sort of see this is one house. They bought the food from the same store. They've all got diarrhea and so have they. You question them and they say, oh yeah, we had some ham at my party. I bought the ham from Coles down the road there. And they go, yeah, so did I. Straight away you go, oh, it's the ham. But when you look deeper and you subtype the organism, subtyped this culprit in this party is a different subspecies or a different serotype. And this is different. So you now know that even though they bought the same ham, they weren't a common source. All the guests here got disease from this strain. All these guests got from this strain, but they weren't linked, even though there was one common factor. So in the end, what they worked out from this example was this was passed on by a carrier who was the host of the party up here, and this one had rat droppings inside the kitchen where they made the sandwiches. So we do serotyping for a reason. Now, in Australia, by law, every time a lab grows a salmonella, it's sent away to a reference laboratory in Adelaide, I think it still is. And the lab in Adelaide serotypes every single one. So we don't do the serotyping. What we do is a polyvalent test. A polyvalent antiserum means it goes positive for all salmonellas. So in my lab in Launceston, yep, it's a salmonella because the API said it was, or the multitoph told me it was a salmonella. I'll check that with antisera, mix, glutination, yep, salmonella. Phone the GP and say, there's salmonella there. Goes away to the reference laboratory, and they then take the time to serotype it properly, and in 2 days' time, I get a reply from them saying it was this serotype or different serotype. And then if we see in the public health system, because not only do we have to send them all away, all the results for salmonella go to a public health lab. And they go, look, in the last 2 weeks in Trevally residents, there's been an outbreak and all these strains are the same. Must be a common source there. If they saw 10 cases but they were 5 different serotypes, there's no panic. If it's one serotype, it means common source is likely. Then they do an investigation. Let's have a bit of a breather because I'm running out of voice power. So by my clock, it's 10 past. We'll come back at 1/4 past. I'm at Thursday still. Okay, now things change depending on where you work. So I'm going to try and teach you the 2 ways that we look for Shigella and Salmonella. The simple thing is, at the moment, every lab looks for Shigella in the same way, but there's now a shortcut for Salmonella. But nonetheless, this scheme here applies to both Shigella and Salmonella. So in some labs it's used only for Shigella, and they got a different way for Salmonella. Other labs use this for both. It's like this. You start off with your poo specimen and you put that on some kind of agar that separates them based on lactose. It may be McConkie agar, but it might be something else. Now, a Mac agar plate is pretty good, but there are better plates that are more selective and more differential. But in the end, the premise is the same. If your bug is a lactose fermenter, straight away it can't be Salmonella and it can't be Shigella. That's great. That's not a bad screen. But all of these only might be, but probably aren't. So your first day screen is to separate the ones that definitely can't be. These might be, but probably are not. And then you would do at least some kind of secondary screen. In other words, apply a small set of cheap, quick tests to these non-fermenters that separate them into can't be Shigella, can't be Salmonella, and then again into maybes. What this screen is depends where you work. But one simple screen that's useful is a urease test, because Shigella and Salmonella are never urease positive, but lots of other bugs that are non-fermenters are urease positive. Please name me, with only 1 millisecond of thought, a common non-fermenter that's urease positive. Pseudomonas is wrong. If I give you a hint, it stinks. Proteus. Proteus is a common non-fermenter that's urease positive. So the urease screen just helps you eliminate the Proteuses. In the past, I've done this kind of screen, where I do a whole range of tests, but they can be done quickly and cheaply. So 2 separate tubes can achieve all of those results, and they're helpful. Because in combination, all those results, either pos or neg in various combinations, can help me make this choice. And once you're as far as here, you then go and do either an API or a MALDI-TOF. So you do at least your primary screen and a secondary screen. Now, the reason we do a secondary screen is what? It's money. Because, just guessing, for every 1,000 non-fermenters, maybe only one ends up being a Shigella or a Salmonella. So if we went straight from non-fermenter to full identification, it's a lot of money. But things do change, because now we've got MALDI-TOF, which can do a full identification for 50 cents. Some labs now just go, nah, if you're a non-fermenter, forget all this screen business. After the first set of screens, there's a non-fermenter, I go here straight away. MALDI-TOF is that quick and that cheap, you can afford now to bypass this. So before, it was an API strip, $5 or $2 even. That's an extra cost, but with MALDI-TOF, this becomes reasonable to do that. But you still need to have this first screen, possibly. Once you're down to here, you can't phone the clinician and issue a report saying Shigella or Salmonella without positive serology. You just can't do that. The risk of your bug not being Salmonella or not being Shigella is reasonably high, because they're often biochemically similar to other organisms. So you need biochemistry plus polyvalent sera at least before you phone the clinician. And then it goes away and is confirmed somewhere else. So we still do that everywhere for Shigella and only somewheres for Salmonella, because for Salmonella there's a better way of doing it now. I'll come back. So okay with that stage 3, stage 4 we're okay. With Shigella there's only 4 serotypes, so there's no need to go to a reference laboratory because you can buy 4 bottles of anti-sera in your lab and just do those 4. But with Salmonella there's hundreds and hundreds of different serotypes. There's thousands of them, and that's just too expensive. What we can do for Salmonella but not Shigella is do enrichment. Here's your poo specimen, and in that poo specimen are thousands and thousands and thousands and thousands of organisms, and maybe a small number of those are Salmonella. To help me find them in culture, if I just put a loop in there and do a streak plate, I might miss that one. So we put this into a broth called selenite broth, and over 24 hours, what this broth does is it lets this grow, but inhibits the other organisms. So it's selective enrichment. And in the end, after these 24 hours, you have not pure, but certainly a much higher proportion of Salmonella than the other organisms. And then you culture that. So you culture it twice. You culture once directly and once indirectly after the broth. But it won't work for Shigella, only for Salmonella. Now, this is new. So we understand that Multitof means we often don't do a secondary screen because it's cheap just to go non-fermenter. Sorry, I didn't know you went back. I would have waited for you if I'd known you went back. So we know now we can do Shigella and Salmonella as a Multitof without doing a secondary screen because it's so cheap. If you've got one. I wonder how many of you will go and work in a lab with Multitof. I mean, they're becoming pretty common. But in Tasmania, there's one in Hobart, but not one here in Launceston. So it depends where you're going to go and work. I guess over time they'll become less expensive and they'll be everywhere. Now, the new agar that's been brought out, and this is just one example from one company, but the technology is going to be applied everywhere, I think, eventually. And it's like this. You want a way to reliably inhibit the growth of non-Salmonella. In other words, E. coli, for argument's sake. So we can find various chemicals that most bugs don't like very much. They grow slowly, but we still want our target bug, Salmonella, to like it and grow really, really well. It's pretty hard to do that. So we've got all these things that do a bit of inhibition of E. coli and a bit of promotion of Salmonella, but not very good. You know how we can make any kind of compound we like to target a certain enzyme? So with the E. coli media for urines, we've designed a molecule with a certain target for an enzyme that only exists in E. coli. Along comes E. coli, hits the molecule, breaks it open, releases a compound that's coloured, the colonies goes blue or pink, whatever they are. So you can make that stuff easily. What they've done with this is the same thing. They've got this inhibitor. This is a poison. This kills organisms. But when it's joined to a second substrate, it's inactive. This is a poison that's not active. And what they do is it's taken into the cell. All cells can take it in, all microbial cells, Shigella, Salmonella, the whole lot. But the enzyme required to break this bond does not exist in Salmonella, but exists in most other coliforms. Not all, but most others, certainly in E. coli. So if you're a bug that can break down this bond, you break it open, this is released, this kills you, and you die. And that means that Salmonella, without this enzyme, isn't killed. Keeps on growing beautifully. But all the bugs you want to get rid of get killed. And when this bug dies, it'll release the excess poison, but the poison by itself in the media can't be taken up by a cell. It's only taken up when it's joined together with the substrate component. Brilliant system. It's so good. Now, last year I decided to change our practice for this topic to use this media. It's expensive, but it's so good. I can take a poo that I've just made positive for Salmonella by putting a bit in there, and I put in maybe 1 Salmonella for every 10,000 E. coli, and you culture it on this media, perfect. It's that good. I mean, I'm really quite embarrassed about how good it is. And if you couple this kind of system with a second one of these that's pigmented, and what you then get is non-salmonellas won't grow because they're killed. Some can still grow, but most are killed. And then you have a second substrate that can be acted upon by Salmonella to make them go coloured. And the other bugs that don't get killed can't do that. So you end up with a system that's very selective. Most bugs are killed, but Salmonella stays alive, and very differential. Salmonella stays and goes blue, and the others that get killed don't go blue. So blue colony equals Salmonella, and it's so reliable. That means in one plate, your blue colony on this plate is so reliable, you can go straight from there to an API or a MALDI-TOF, and then to serology. So it speeds the whole thing up. It's really useful. And I suspect that over time this will be applied to other organisms. The key thing is finding some kind of enzyme that's specific for your organism. But it's a great system. Good one at a time. Okay. Talking now about a special kind of infection with Salmonella. And in these cases, it's where the disease is not only in your bowel, it's also in your bloodstream. You still acquire the bug by ingestion, but diarrhea is not the primary symptom. And in fact, quite often with typhoid fever, you don't get diarrhea initially. So there are some that cause enteric fever. Enteric fever really means you've got some diarrhea plus a temperature because you've got bugs in the blood. Paratyphi A, B and C and Salmonella cholerae are all capable of being invasive. But the disease is comparatively mild. The one we'll talk about more about is this one. So typhoid fever now becomes the separate topic to discuss. With typhoid fever, it's primarily a blood-borne disease, not primarily a gastro disease. Salmonella typhi has a particular antigen on its surface which makes it virulent, which is what's called the VI antigen. So the VI antigen is what's called the virulence attribute. It's a capsule. Salmonella typhi got a capsule that lets it become invasive. And it's also possible to get chronic disease and become typhoid Mary because the bug goes from your bloodstream often into your gallbladder and stays there and is secreted out into your gut on a slow, dripwise fashion for a long period of time, even though you've recovered from the disease. As we move on, make a point of this in your head. It's very uncommon to have Shigella or Salmonella in your blood. So a positive blood culture that grows a Shigella or a Salmonella is a real cause for concern. If I go to E. coli from blood, I go, it's E. coli septicemia. So what? UTI, bloodstream, septicemia. It means the person is sick, but it doesn't indicate anything underlying this sinister. If you have Salmonella or Shigella in your bloodstream, something sinister is going on, like HIV, or some other underlying severe immunosuppression. These bugs do not normally go into the bloodstream. Look now at typhoid fever. And I want you to start this whole looking at this chart, starting up there. So you ingest the organism, and what you'll see is on the far outside, there's a long period in which you are asymptomatic. This long period here with this broken line is where you have no symptoms yet. So you ingest the bug, and the starting point is it grows inside the small intestine and invades the cells around the gut in the lymph nodes, and you have a small period in which the bug goes from lymph nodes via the blood. You have this transient bacteremia. But here, there's only a small number of bugs in your bloodstream, not many. So you aren't sick. This is a very mild, bit of a fever, a bit of headache, don't feel very well, but you're not acutely sick. And then it ends up being taken up by the macrophages in the liver, the spleen, and the bone marrow. And this is the point at which you first become sick. So now you've got true septicemia. Bugs in the blood up here was small number and transient. Now it's large number and they're active. You now have septicemia, and you get rose spots, which means you're bleeding under the skin. You get the fever, other organs are infected. You are now acutely sick. This is typhoid fever. Then the bug comes out in your bile and then goes back into your bowel a second time. And normally you don't get diarrhoea until the bug's in your bowel the second time. So diarrhoea is not an early feature or even a common feature of typhoid fever. The hallmark of typhoid fever is septicemia. Now, once you have typhoid fever and you recover, you form antibody against the capsular antigen of the organism. So you become immune. But if you're immune and the bug's stuck in your gallbladder, there isn't much action in the gallbladder. So as far as your antibody cleaning up your gallbladder, it doesn't happen. But it means the bug can't reinfect you, but you keep on passing it out. So you can become a carrier, a long-term carrier. And without antibiotic therapy, you won't become a non-carrier, because the bug just lives there in your gallbladder and stays there. In your gallbladder, it's free from attack from your antibodies, happy in there, just pops out in your bowel, and you pass it out and you're a carrier. Look over the time, how do you diagnose typhoid fever? Well, the key thing is looking here at the point at which you ingest the organism, and see what happens after you ingest it over this course of a number of weeks. So you do form antibody to the capsule, but not for about a month. So doing a blood test looking for the antibody to the capsule is helpful, but not until later on in the disease. The stool being positive occurs quite early when you first ingest them, but right here you aren't sick. So by the time you're sick, the period which it's in your stool has passed. So you're sick here. There's no bug there anymore. So the best thing to do for diagnosis of the disease is you're sick and your blood culture positive. So the blood culture, culturing the person's blood, is the best and quickest way to diagnose typhoid fever. Stool culture is unreliable because most often at the time you first become sick, you're stool negative. Typhoid fever is diagnosed by blood culture, and then it helps to be able to show the antibody, but the real hallmark is a POS blood culture. Now, I think in the news, in the last couple of, I must have a look, check when I get back to my office, there's been an outbreak of typhoid fever, I think, in New Zealand. Anyone heard that? No one knows where it came from. It may have been a returned traveller. Now, in Australia, typhoid fever is not endemic. There is no endemic salmonella typhi in Australia. Remember, this bug is only human. There is no animal source. So typhoid fever is always passed on human to human. If you see a case in Australia where it's not endemic, it's a big deal. Because one person who's a carrier in the wrong situation can soon pass it on to a whole bunch of other people. And this is now a fecal oral transmission of a pathogen which causes bloodborne disease. You think about normally with septicemia. If I've got septicemia, I'm really, really sick. But the bug is now in my bloodstream. I can't pass it on. If right now I had E. coli septicemia, no one is at risk. It's in the bloodstream. I can't get it to you at all. With typhoid fever, it's septicemia, and I'm shedding the bugs at the same time in my stool if I'm a carrier. So it's more contagious and it's more risky. So typhoid fever is always a big deal. If there was a case diagnosed in Tasmania today, tomorrow it would be front page of the paper. It's uncommon and it's a big deal. Public health wise, it's a big deal. I mean, how often do you see on the newspaper front page, E. coli causes septicemia? No one cares. It happens all the time. But this would be a big deal. Right, last little thing to think about now are the Vibrios. Vibrios are certainly gram-negative rods, but they're not coliforms. They're oxidase positive, they're facultative, and they're fermentative, but they're not coliforms. They grow really, really well. They're rapid, vigorous growers. They tend to give bigger colonies than coliforms. They grow big, quickly. And most require some kind of salt in the media, which is easy because almost all media that we make up is based on normal saline. The amount of saline in most kinds of culture media is enough salt for Vibrios to grow. But some need more than that, but most don't. Most grow with what the salt is in the background of most media. And their habitat is marine. These are aquatic organisms. Their normal habitat is the water, either fresh water or more commonly salt water. They don't hang around in the bowel in the absence of disease, whereas coliforms do. Coliforms, Shigella salp, the bowel is their habitat, but these bugs are marine, they live in the environment. It just happens that a couple of them can cause disease. So there are a couple of ones that are really important and an extra one that's less common but pretty important as well. So Vibrio cholera causes cholera. Cholera can be two kinds of cholera. It can be epidemic cholera. That is, bugs that are highly contagious, really well adapted, and they cause disease in massive outbreaks that cover the whole country. So we talk about big global pandemics of cholera that last for decades at a time. These are successful organisms that get around. We also have cholera that occurs just sporadically. It's not impossible to get some cholera tomorrow. This is just a one-off. There's two kinds: pandemic and just sporadic cases. Parahemolyticus is again a bug from the environment, but can cause little episodes of gastroenteritis linked to seafood. You wouldn't get Vibrio parahemolyticus from a meat pie. It's got to be seafood because this is an aquatic organism. And then Vibrio vulnificus is a separate case because it doesn't really cause gastroenteritis, but it is acquired via ingestion. But the primary disease is rapid onset septicemia with frequent death. It's not a nice organism. It tends to affect people either from ingestion of poorly controlled seafood or by contact with water. But the primary disease is septicemia, and people lose limbs and they go into septic shock. It's very, very aggressive. There aren't many bugs I'm scared of, but that's one of them because it's so aggressive. And you see it really, a lot of it happens in America, on the Gulf Coast, And it's linked to where the water's very, very warm, and you get lots of this bug, almost having little blooms of growth in the water. So at the moment, these bugs are so uncommon in Australia, they're not routine looked for. You look for these bugs only if there's some sort of indication in the history. So what do we know about cholera as an organism? The truth thought about cholera to people evokes the idea that people are acutely sick. They've got such horrible diarrhoea, they're dying from dehydration. But most people that get infected have quite mild diarrhoea. It's only a small number that get the really bad disease. And again, it really depends on the person. We see cholera epidemics in areas where there's poor nutrition. Now, there have been studies that have been done in healthy volunteers where you need to ingest thousands and thousands and thousands of organisms. In fact, when they first tried this experiment, they couldn't believe the results, because the results meant that if you were healthy and you drank some cholera, you didn't get sick. And the numbers of bugs required to make you sick meant that to catch cholera in the environment in normal situations, you'd have to ingest almost pure feces from somebody that was sick. It didn't make sense. And the problem was, healthy volunteers are not a good model for the people that are exposed to cholera in a natural outbreak. Healthy volunteers are usually young men who are healthy, want to be a spare cash, and they're well nourished, good stomach acid. We see cholera outbreaks, it's normally in third world countries where the people are malnourished and don't eat much because there's no food, and therefore their baseline stomach acidity is terrible. In those people with no stomach acid, the dose required is very, very low. And that's why cholera is so rampantly infectious in those environments, because you need to ingest a very small number and you can soon get back into your water source so quickly. So there have been lots of pandemics. These are global epidemics. So just this century, 20 million people have died in India alone, just caused by cholera. There have been a couple of great big outbreaks in the last decade that have made lots of space in the press. So Zimbabwe had a big outbreak, but the one that I found most amazing was the one in Haiti after the earthquake. You may have heard this story before, but what was amazing, so post-earthquake, the country's already got people who are fairly malnourished. Earthquake, loss of all infrastructure, no clean water to drink, lots of contamination with sewerage. 120,000 people in a small space of time all caught cholera. And when they screened and looked at the strain more carefully, the strain of cholera that these people had was not endemic to Haiti. And this is the scary thing. The cholera that these people caught was brought in by the aid workers who came to Haiti to help clean up the earthquake. The strain was imported by aid workers. Now, with cholera, you do develop some kind of immune response, so that you tend to have a limited immunity to the strain that's endemic in your area. It's not protective, but it means if you get cholera to your endemic strain, you have some prior memory and your disease is fairly moderate. You bring in a whole new strain that your community's not seen before, there is no baseline immunity at all, and you all get rampant, rapid disease. And in that kind of environment, post-earthquake, no infrastructure, no healthcare, no clean water, you can soon see why it exploded to be such a massive outbreak. And that all occurred, I think, in about 3 or 4 months. It was a huge thing. And there was lots of then, after the event, lots of finger pointing and compensation claims about who caused the outbreak, because it was brought in by aid workers. So it was quite a complicated story. Almost finished. So I've done this before already. So we know about the fact that the flagella on cholera is what lets it attach to your bowel wall. So when you have a vaccine to cholera, the vaccine targets the flagellal antigen. If your antibody that you have in your bowel binds to the flagella of the cholera, it can't attach. If it can't attach, it can't secrete toxin for your cells to absorb. So it's helpful, but not totally protective. The cholera toxin, what it does is it stops your cells absorbing water, and it makes your cells actually secrete water. So you lose fluid twice. You can't absorb it, and you secrete it. So you're losing intracellular fluid. That's why people die. Dehydration. We also know that the bug can become dormant in the environment. It's possible to find Vibrio cholera in the environment, inside plant cells, inside algal cells, inside ship's ballast tanks. You can transport cholera all around the world in ship's ballast tanks, because ships take in water into their tanks to make sure they're stable, get in the port and pump them out again. So if you're in port in India somewhere, you pump a whole lot of water in, sail to Australia, get to Australia, pump it all out again. But you notice how much gets transferred around by ballast tanks. Okay, we can serotype Vibrio cholera. Serotype 01 has an association with the genes that code for toxin. They are not physically linked. So having the 01 serotype does not mean you will have the toxin. And not having the 01 serotype does not mean you can't have the toxin. But for some reason, there's a very strong association. If you have the 01 serotype, you're probably toxin positive. Probably. But 02 and 03 and 04, all the way to 0138, probably haven't got toxin. They cause disease still, but not the rapid disease, which is massive true cholera. The 0139 was a strain that emerged in the Bay of Bengal earlier this century. And the 0139 serotype is the 01 serotype with a couple of mutations in the gene that codes for the flagella. So it's a whole new serotype, but it really is the old 01. So the 01 and 0139 that both have a strong link to toxin production, and the ones in the middle don't. So 0139 is a new version of the 01. What made it so nasty was, if you make an immune response to the flagella and it mutates to become a new flagella, the old immune response doesn't work anymore. So all of a sudden we had a bug that was now endemic in an area where the people had no background antibody, which is why it's such a successful organism. If you have a non-01, that is 02 to 0138, they tend not to make toxin and they cause fairly mild disease. So always, if you say, oh, I've got cholera, or I've grown a cholera from this person's stool, the first question is it 01 or 0139 or the rest? That's the first question you want to ask. To diagnose cholera, if it's true cholera, then clinically it's distinctive. Cholera diarrhea isn't just diarrhea. It's so bad you're passing out in the end, you can't retain any fluid at all. And you're passing out poo, which isn't even brown anymore. It's just like water. It's so rampant. If you want to culture it, you culture it on TCBS media. TCBS is thiosulfate, citrate, bile salt, sucrose agar. The TCB part of TCBS are selective. Good, freshly made TCBS agar will not support the growth of most coliforms. If it's old agar, it will, but freshly made TCBS is very selective. And only Vibrio-type organisms, Vibrios and Aeromonas, for example, will grow. And the sucrose is because Vibrio cholera is sucrose positive and goes yellow. The plate's green. And a positive sucrose fermentation goes yellow. And most choleras are going to be yellow. If you're culturing someone's poo in Australia with TCBS and you grow a green colony, you don't throw it out. Because growth on TCBS means it's a Vibrio, most likely. And in Australia, any Vibrio is important. The only time that the algorithm is TCBS growth, green, chuck out, yellow, keep, is where you've got a known outbreak of cholera and you're targeting only Vibrio cholera, which is yellow. But in a sporadic case in Australia, where someone's got diarrhoea, your question is, do they have Vibrio of any kind? Because Vibrios are not common in the bowel. But where cholera is endemic, your question is different. Your question is, does this person have this horrible endemic strain of cholera? If yes, I want to know. If no, I don't care. So the care factor is different. In an outbreak, do you have the outbreak strain? So yellow only. In this situation in Australia, where it's just a sporadic case, it's what's wrong with you? It's a different question. And again, once you grow a Vibrio, you do Multitoph or API, give it a name, and then if you do grow cholera, you have to go have it serotyped. If you grow me a cholera, my first question is it O1, O139, or the rest? And you can't do that with a Multitoph or anything else. It's got to be done by serotyping. So that's cholera. That's feces. You pass that so much liquid, you're passing it 10 to 20 litres per day, and your poo stops being brown because you can't eat anything anyway. Nothing stays in. Oh, there's more to do. Gee. I better stop, and what can I do? I'll try and catch up these next two slides at the start of next time's lecture. So it's your job, when you get sidetracked, to say, Stephen, stop talking, get back on track. Because I'm going to over time today. Don't forget, this Wednesday, it's the test.